Google Chrome is one of the most famous browsers in the world, and its security has already been investigated by many security researchers. Today I'm going to discuss a V8 interpreter bug, which is the JavaScript interpreter of Google Chrome. And this bug can finally cause remote code execution. Here is a brief overview of the contents. Firstly, I'm going to discuss some V8 descriptor array basics that is needed to understand the bug. And I'm then going to discuss the root cause of the bug and the effect of the bug. Then I'm going to discuss the exploitation, which is using the heap spray to obtain object faking primitive. And I'm going to exploit the object faking primitive without any address link. Finally, I'm going to discuss the fix about this bug. I'm a former security researcher at the Pangu team, in which this work is done. And I'm currently a PhD student at IUB, advised by Professor Xiaofeng Wang. I'm an alumnus from Imperial and the CTF player at Reka Peak. In V8, JavaScript object has an object map that is used to store the shape of an object. It contains a descriptor array pointer, and this descriptor array is used to record the layout about the property field, and which is the shape about the property. And here is an example. We create an object here and debug print its structure, and within the map structure it has instance descriptors with type descriptor array. And we are going to investigate this structure. So if we look at this structure, it contains some information about the property, and the property string A, B, C are here. And it also contains a data field 0, 1, and 2. This is the field index of each property, which is the position of the property. And here is a structure of the descriptor array from V8 source code. It contains a header with 64 bits. It also has many element part. It has many elements. Each element has 3 parts. The first part is a key, which is a property string. The second part is a descriptor detail, which is a bit encoded information about this property. So here we only care about the field index. The field index is 20 bit to 29 bits in property details. And let me have an example for this. The memory layout of the descriptor array is shown here. The header is a white line, which has 64 bits. The blue line is a string of each properties, A, B, and C. And the red line is the field indexes, 0, 1, and 2. And there are 3 elements in this descriptor array. So what is this field index? The field index is not the index to property array. It's an index to in-object property plus the property array. So if we look at the picture here, the in-object property lies just after the object, and the property array is a pointer that points to a fixed array class with many properties stored in the property array. So when we are fetching a field from an object, this pseudocode illustrates the idea of the relationship between the field index and the in-object property and backing store properties. If the field index is smaller than the number of in-object properties, it will just return the in-object field index, and otherwise it will subtract the in-len from the field index and use this as an index to backing store properties. So if we go back to example before, we have A, B, C with field index 0, 1, and 2 respectively. So 0, 1 is smaller than 2. The example here has two in-object properties. So A and B are here. And since 2 is larger and equal than 2, so the C will be stored in the property field, in the backing store property array. The problem is caused when uint8 array with 2 to the 32 length is allowed. So this causes problem when we access uint8 array with this numeric string and know the value of this numeric string is 2 to the 32 minus 1. And before we get into the actual vulnerability, let's look at some property access bytecode in V8, because this is a V8 interpreter bug. So, and this interpreter is related to these two kind of property access bytecode. So first one is LDA named property. It is generated for named access like this. And another one is LDA keyed property. This is generated for index access like this with a value in the inside the bracket. And note that when the things in the bracket is numeric string like this, it is still a LDA keyed property instead of a LDA named property. However, when the value of numeric string is too big, LDA named property is generated. So for example, when the value is larger than 2 to the power of 32 minus 1, it will generate LDA named property. So the access that causes the vulnerability will generate LDA named property, and this is the call chain that causes this bytecode to be generated. So visit property load is a abstract syntax tree visitor function, and it will finally call the string to index, and this function will judge this if the value is larger than this value, and if it is larger and equal than this value, the LDA named property will be generated. And when executing this bytecode in V8 interpreter, the handler will finally call the load IC load function with a property name this numeric string. So in load IC load, a class is used. This class is a class used to find element or property stored in V8 object. And for access, like for the vulnerable access, the name here will be this numeric string, and the object here will be the ARR object. And the problem is these two lines of code create lookup iterated instance with index equal to this value and number.entry equal to this value, which is 2 to the power of 32 minus 1. And load IC load generates the following function call. And within the get field index, this debug check fails. So if we look at the isElement function, it firstly check if the index is smaller than kmax array index, which is false in this case, in our vulnerable case. And however, for the second condition, it will return true because it is not equal to k invalid index and it has typed array elements. So the return value of isElement will return true, which does not satisfy such debug check. So in summary, intuitively, the LDA named property, which is used to handle named property access, is generated for an element access. However, in handler of LDA named property, there is no corresponding code that handles the element access case, because it assumes it to always be named property access. So such the debug check assertion fails. Now we already have the debug check failure, and the next problem is what such debug check failure can cause. So before that, we are going to look at the lookup iterator again. This class can have different interpretation. So the key is the result of each element decides how number field is interpreted. If the each element returns true, the number will be the index to the array element. So if the each element is false, the number is the index to the descriptor array. And the problem is, due to this bug, the V8 interprets the index to array element, which is this value, as the index to descriptor array. So in this case, this value is used as index to descriptor array, and which is actually wrong. And since this value is used as signed integer, it is actually a -1 index access. And therefore, the overall effect is field index will be fetched from descriptor array with -1 index access. And here is some source code about the content that I have just covered. You can look at it if you are interested. So the -1 descriptor array index, it always lies in the header of the descriptor array. So if we remember the structure of descriptor array covered in last part, we can know the header contains this following contents. And field index will overlap with the alignment filter in the header, which is this part in the red rectangular. And remember, the field index is 20 to 29th bit of the second double word. And but unfortunately, we cannot control it, and it is always 0. So however, if there is no property, we can have an out of bound. And we can see here the 64-bit to 48-bit is alignment filter, which overlap with the second word of 20th bit and 29th bit. And here is the illustration of the memory layout of descriptor array above. And when we access the descriptor array with -1 index, the stuff in the yellow rectangular is a fake field, is a fake element of the descriptor array. The red line is the fake field index of a -1 or out of bound access. Unfortunately, this value is always 0, and we cannot control it. And finally, you can get into the proof of concept. We firstly create a unsigned int 8 array with this length and access this property. And we just call it in a while loop and debug print the return value of this. So in the debug mode, the debug check will fail, as we have covered in the last part. But in the release mode, this map will be printed. If you are familiar with V8, you will know that such a map object cannot appear in the JavaScript variable. So this is obviously caused by one block out of bound access of the property array. But this property array points to read-only pages, and this value will always be constant, and which I will cover in the next part. Now we already have the out of bound access in a property array. However, this is not very useful. So what we are going to do in this part is to use the heap spray to have an object faking primitive. Currently, out of bound only occurs in the property array. However, this is useless because when number of property is 0, property pointer points to a fixed array 0, and this is a constant pointer in read-only page, and so which is not on the heap. And thus, when one block out of bound occurs in this fixed array 0, we can only read the next map pointer, and this is always a constant value because it is on a read-only page. And this map pointer is actually the map pointer that we have obtained in the proof of concept in the last part, which is this value. So let's have a illustration for this. Firstly, we create an empty object, then we debug print it, and we can see the property points to this fixed array 0, and this fixed array 0 lies in a read-only page, and its out-of-bound access can only read the fixed map pointer, which is not useful for our exploitation. So what we want is not an out-of-bound at backing store property array. Instead, we want out-of-bound at the in-object property, which is on the heap. And we also want the next block is controllable so that we can actually read an arbitrary content as a pointer. The approach is use the inheritance. We create a class array that extends int 8 array, and use this child class instead of the parent class in the exploit. So when we use the inheritance, there will be in-object property. So let's have an illustration again. We create a class ARR, and we create an instance for this child class. If we debug print it, we can see that in the map structure we have in-object properties 10, which means it has in-object property. And before going to the exploitation, another point to note is that V8 will shrink the unused in-object property when they are not used for many object instance creations. This is used for memory optimization. So because if in-object property of an array is not used for many creation, it means that it will not be used. It's not very likely to be used in the future. So this is actually a optimization in V8. And the following code illustrates the idea. In a for loop we create a ARR and debug print it. So initially the output will give the in-object properties 10, which is not shrinked. And however, after a few iterations, since we haven't used the in-object property, the in-object properties is shrinked to 0 by V8. So finally, we can get into the exploitation idea. Firstly, we make an inline cache for this vulnerable numeric string key at first in-object property block. And then we shrink the in-object property use the technique in the last slide. And so inline cache from 1 causes out-of-bound access. And therefore, newly allocated instance can have out-of-bound access read, and it can read the unallocated block, whose content can be spread beforehand because the heap can be actually spread before the exploitation goes. So we actually can control such unallocated block. And a key point to note is that inline cache must be created before shrinking. And here is a fake object function. Firstly, we create an ARR with array buffer with size. The size of this array buffer is 2 to the power of 32. Then we use a for loop to access the vulnerable numeric string key. And since we have accessed this for many times, the inline cache will be created before shrinking. If we don't have this loop, this cannot be achieved. Then we just return the ARR and this for the vulnerable numeric string key. So now we already have the arbitrary object faking primitive. However, the problem is we cannot have any address leak in this case. So in this part, I'm going to cover how to use the pointer compression feature to exploit the object faking primitive without any address leakage. First of all, let's review the normal exploitation that uses the address leak. Firstly, we leak the address of some object, for example a double array, by reading its pointer as a double floating point number, so that after decoding such double floating point number, we can have the address of this object. Then we fake an object using that double array. In the third step, we read an unboxed double as pointer, which points to our faked object. So in this step, we regard an unboxed double floating point number as a pointer. So the problem is, what if we cannot achieve step 1, and which is the case in this vulnerability? So the thing is, we need to exploit the pointer compression feature, and which is a new feature in V8. In this feature, addresses of all V8 objects share the same high 32 bits. It stores each address in the memory as an offset to base address, which is a low 32 bit. So therefore, V8 only needs 32 bit to store 64 bit pointer, and this saves half of the memory. And the point to know is that the base address, which is a high 32 bit, is randomized. And we are going to leak this address later. So there is no random, and however, the fortunate thing is there is no randomization for low 32 bits stored in the memory. For example, the map address are constant values, like the unboxed double array map and the map of array buffer. However, backing store of array is still somewhat randomized since heap is very messy. Fortunately, this can be solved using a huge array. So let's have an example for this. And firstly, we create an array with very large size and fill it with a floating point number. Then we debug print this array. And in the element field, we can see that the low 32 bit of the address is always a fixed value in different rounds. And this means we can use this, we can exploit this address to fake an object in this fixed double array. So the reason for this is that V8 allocates a separate page for backing store of huge array, whose offset to base address is not randomized. Thus, we can fake an object and fetch the fake object using a technique that we covered in part 4. So now we already have a fake object primitive. And one thing to note is that we can just modify its content by modify content in the huge array to change it to another object without triggering the bug again. So part 4 only needs to be triggered once. And here, and after we have a fake object, here is the exploitation steps. Firstly, we fake a double array and point its element backing store to the header of the huge array backing store page. This header stores some meta information, and in this meta information, the base address, which is a high 32 bit of address, is stored, and we can leak the base address here. Secondly, we fake an object array and store the WebAssembly function into its elements. Then we read the huge array, so that in this way we can leak the WebAssembly function address. And then finally, we can fake a uint32 array to achieve arbitrary read and write primitive. Once we get arbitrary read and write primitive, we can have a normal exploitation. We firstly read the WebAssembly function, and to read the read-write executable page and write the shellcode to it, and then execute the WebAssembly function to execute our shellcode. Finally, I'm going to briefly discuss the fix of this vulnerability. And as we can see, the its element case is handled in ic.cc, which means the its element can already be handled in LDA named property. In this way, it always goes to the load slow case, which is a V8 slow step. So in this way, the bug can be fixed, and that's all of my presentation.